The universe is a vast and mysterious place. It is filled with billions of galaxies, each containing billions of stars. Stars are the building blocks of the universe. They are giant balls of hot gas that emit light and heat. Stars are born, they live, and they die. Their life cycle is a fascinating story of cosmic evolution. Nebulas are the birthplaces of stars. These vast clouds of gas and dust are scattered throughout the universe. They are composed mostly of hydrogen and helium, the two most abundant elements in the cosmos. Nebulas are often illuminated by the light of nearby stars, creating breathtaking displays of cosmic beauty. Within these nebulas, gravity acts as a sculptor, slowly shaping the clouds into denser regions. As the gas and dust clump together, their gravitational pull increases, attracting even more material. This process of gravitational collapse is the first step in the formation of a star. It's like a cosmic snowball effect, with the snowball getting bigger and denser as it rolls downhill. As the cloud collapses, it heats up due to the increasing pressure. The temperature at the center of the cloud can reach millions of degrees. This intense heat triggers nuclear fusion, the process that powers stars. When hydrogen atoms fuse together to form helium, they release enormous amounts of energy, igniting the star and making it shine. The initial stage of a star's life is called the protostar phase. A protostar is a hot, dense ball of gas that is still collapsing under its own gravity. It is not yet a true star, as it is not yet hot enough to sustain nuclear fusion in its core. Think of it as a star in the making, like a lump of clay that is being molded into a beautiful sculpture. As the protostar continues to collapse, its core temperature and pressure increase. Eventually, the core becomes hot and dense enough to ignite nuclear fusion. At this point, the protostar becomes a main sequence star. It is now a stable star powered by the fusion of hydrogen into helium in its core. This is the longest stage of a star's life, and it is the stage where our sun is currently. The main sequence is a period of stability for a star. It is a delicate balance between the inward pull of gravity and the outward pressure generated by nuclear fusion. This balance keeps the star from collapsing under its own weight or expanding into space. Imagine a tug of war between two equally strong teams, with neither side able to gain an advantage. A main sequence star is a star that is in a state of equilibrium, fusing hydrogen into helium in its core. This is the longest and most stable stage of a star's life. Our sun is a main sequence star, and it has been in this stage for about 4.6 billion years. It will remain in this stage for another 5 billion years or so. The size and brightness of a main sequence star depend on its mass. The more massive a star is, the hotter and brighter it is. Massive stars burn through their hydrogen fuel much faster than smaller stars. Imagine a car with a larger engine burning through fuel more quickly than a car with a smaller engine. The main sequence is a period of stability for a star. However, it is not a static state. As a star fuses hydrogen into helium, its core slowly contracts and heats up. This causes the star to become slightly brighter over time. It's like a campfire that slowly burns hotter as more wood is added to the flames. When a star runs out of hydrogen fuel in its core, it begins to fuse heavier elements, such as helium and carbon. This causes the star to expand and cool, becoming a red giant. Red giants are much larger and cooler than main sequence stars. They are also much brighter because they have a larger surface area emitting light. Think of a balloon being inflated, becoming larger and thinner as it expands. As a red giant expands, it sheds its outer layers into space. This creates a beautiful cloud of gas and dust called a planetary nebula. Interestingly, planetary nebulae have nothing to do with planets. They were named this because they often look like planets through early telescopes. The core of a red giant continues to contract and heat up. Eventually, the core becomes hot enough to fuse carbon into heavier elements, such as oxygen and neon. However, this process does not release as much energy as hydrogen fusion. Eventually, the core runs out of fuel and can no longer support itself against gravity. Massive stars end their lives in a much more dramatic way than smaller stars. When a massive star runs out of fuel, its core collapses under its own gravity. This collapse happens so quickly that it triggers a shock wave that rips the star apart in a massive explosion called a supernova. Supernovae are the most powerful explosions in the universe. They can outshine an entire galaxy for a brief period of time. Imagine a firework exploding with such force that it illuminates the entire night sky. During a supernova, the core of the star is compressed to incredible densities. This can create a neutron star, a tiny, incredibly dense object made entirely of neutrons. Neutron stars are so dense that a teaspoonful of neutron star material would weigh billions of tons. If the core of the star is massive enough, it can collapse into a black hole. Black holes are objects so dense that not even light can escape their gravitational pull. They are the ultimate cosmic enigmas, and they continue to fascinate and challenge our understanding of the universe. White dwarfs are the remnants of stars like our sun. They are incredibly dense and hot, but they no longer produce energy through nuclear fusion. White dwarfs are about the size of Earth, but they can have as much mass as our sun. Imagine squeezing the entire mass of the sun into a sphere the size of Earth. Neutron stars are even denser than white dwarfs. They are formed when the core of a massive star collapses during a supernova. Neutron stars are about 20 kilometers in diameter, but they can have twice the mass of our sun. Imagine squeezing twice the mass of the sun into a sphere the size of a city. Black holes are the most extreme objects in the universe. They are formed when the core of a very massive star collapses during a supernova. Black holes are so dense that not even light can escape their gravitational pull. They are invisible to telescopes, but their presence can be inferred by their effects on nearby matter. Imagine a bottomless pit that swallows everything that comes too close. The death of a star is not the end of the story. The material that is ejected during a supernova or shed by a red giant enriches the interstellar medium, the space between stars. This material can eventually form new stars, continuing the cycle of stellar life. It's like the cycle of life on Earth, where the decay of organic matter provides nutrients for new life to grow. The heavy elements that are created in stars are essential for life as we know it. The carbon, oxygen, nitrogen, and other elements that make up our bodies were all created in stars. We are all made of star stuff. The study of stellar evolution helps us to understand our place in the universe. We are all part of a grand cosmic cycle, a cycle of birth, life, death, and rebirth. The life cycle of stars is a fascinating story of cosmic evolution. From the birth of stars and nebulas to their dramatic deaths as supernovae, stars play a vital role in the universe. They are the building blocks of galaxies, and they create the heavy elements that are essential for life. We are all connected to the stars. The atoms in our bodies were once part of stars that lived and died long ago. We are all made of star stuff, and we are all part of the grand cosmic dance. The study of stellar evolution helps us to understand our place in the universe. It reminds us that we are part of something much larger than ourselves, something that has been unfolding for billions of years and will continue to unfold for billions more.